Today, we are diving into something that honestly feels like it's straight out of a spy movie. We're talking about a way to secretly teach an artificial intelligence to lie. We're going to explore how just a handful of corrupted images can trick a super powerful AI into looking at a truck and confidently calling it a bird. Okay, let's jump right in.
So let's just start with that central question, one that sounds like it's pure science fiction. Can you actually force an AI to see something that just isn't there? I don't mean just make a random mistake. I mean, can you make it confidently believe a lie?
Well, the answer, according to the research we're breaking down today, is a huge yes. A really sophisticated state-of-the-art image model can be poisoned while it's learning. It can be manipulated to look at this very picture of a truck and declare with total certainty that's a bird. How on earth is that even possible?
And look, this isn't some hypothetical theory. The researchers who actually found this vulnerability, they lay it out plain as day. They discovered a method to manipulate a model so that it will misclassify any image you pick and turn it into any category you want. It's targeted, it's precise, and it's incredibly sneaky. So how does it work?
The key to this whole digital heist isn't about, cracking the AI's code. It's about exploiting the very way it learns. And the open door for the attacker is this super powerful technique where the AI learns without having all the answers fed to it.
It's called semi-supervised learning. And, think about it. Having people sit there and manually label millions of images, it's crazy expensive and slow. But there are literally billions of unlabeled images just sitting on the internet, totally free. This technique lets an AI learn from a small, trusted set of human-labeled pictures, and then use that knowledge to go out and learn from a gigantic, untrusted pile of data from the web. And here's the really critical part. The AI is basically teaching itself. It looks at all those unlabeled images, it makes its best guess about what's in them, and then it uses those very guesses to get smarter. It's this powerful feedback loop where the AI is its own supervisor.
And that, right there, is the vulnerability. The AI just assumes all this data it's scraping is legit. But what happens if an attacker has secretly seeded that data? What if some of it is a carefully designed trap, made to look innocent, but built with one malicious goal?
This is where the heist really begins. The attack itself is actually brilliant in how simple it is. It's not about brute force. Instead, it creates this subtle, poisoned path for the AI to follow, a path that just gently leads it to exactly the wrong conclusion.
So imagine that wavy line is the boundary, right? It's where the AI decides if something is, say, a truck or a bird. A normal mistake might be one data point just falling on the wrong side. But this attack doesn't just drop in one bad apple. No, it inserts a whole chain of them, a path, that slowly, gently pulls that decision boundary way over until it captures something it absolutely should not.
Now, this whole thing works because of a core rule in modern AI design: smoothness. The best way to think about it is like a volume fader on a soundboard. You nudge it up just a tiny bit, the volume goes up just a tiny bit. You can't just jump from silent to max volume instantly. AI is designed the same way. A tiny change in an image should only cause a tiny change in its guess. This is normally a good thing. It makes the model stable. But the attack cleverly exploits this very rule by making a long series of these tiny connected changes.
So what does this poison path actually look like? Well, the attackers create what they call a bridge of images. They start with a real picture of a bird, we'll call that the source, and the picture of the truck they want to misclassify, that's the target. Then they use an algorithm to create a whole series of blended images in between, where each image is just a tiny bit different from the one before it.
So during its training, the AI sees the first image on this bridge, which is pretty much a perfect bird, and it correctly thinks bird. Then, because of that smoothness rule, it sees the next slightly morphed image and thinks, yep, that's also a bird. And as this chart shows, that poisoned bird label just propagates down the chain, step by step, image by image, until the AI gets all the way to the end of the bridge, the actual picture of the truck, and confidently calls it a bird. And just like that, the heist is complete.
Okay, so we know how the attack works. But the truly shocking part of this whole thing isn't just that it's possible, it's how ridiculously effective it is and who it works best against.
Get this. To pull off the entire attack, to make an AI see a truck as a bird, the attacker only needs to poison 0.1% of the unlabeled data. That's just one malicious image path for every 1,000 clean ones. It's an incredibly small, almost invisible footprint.
But here is the real kicker. You'd think a smarter, more accurate AI would be harder to fool, right?
Wrong. This graph shows the complete opposite. Down at the bottom, the x-axis is the model's accuracy, so further to the right means a smarter model. The y-axis on the side shows how well the attack works. And as you can see, the most accurate models are also the highest up on the graph. That means the attack is more successful against them. The very smoothness that makes them so good also makes them better at learning these sneaky, malicious patterns. It's a total paradox.
So, yeah, the situation seems pretty bleak. We've got a stealthy, super effective attack that works best on our best models. But the same researchers who found this problem also came up with a pretty clever way to defend against it. And it's less about checking the data itself and more about watching how it behaves.
The best way to get this defense is with a social network analogy. Think of each data point like a person. Normal, good data points are like regular people. You know, their opinions are shaped by lots of different friends and influences. But the poisoned data points, they're different. They form this tight, isolated clique. They only listen to each other, they stubbornly stick together, and they pretty much ignore what everyone else thinks.
So the defense is basically to monitor these social dynamics during training. Instead of just looking at the raw images, the system watches how the AI's opinion of each image changes over time. It's essentially building an influence map, tracking which data points are affecting the labels of which other data points.
And this graph, this is the aha moment. All the normal, benign data points, that's that huge blue cluster. They have a really wide, diverse range of influences, exactly like you'd expect. But the poison data, that's the tiny orange spike, completely separate from everybody else. Their influence patterns are so weird, so insular, that they stick out like a sore thumb. They form their own little island, which makes them easy to spot and then just remove.
And what's really fascinating is that even when the defense isn't 100% sure, it finds something useful. The benign data points that it flags as kind of suspicious are almost always near duplicates of other images in the dataset. They form their own tiny, natural cliques, which just proves the defense is doing its job right. It's correctly identifying these tightly grouped, insular data patterns.
So, after all of this, the heist, the paradox, the detective work, what's the big picture? What's the final takeaway from all this for the future of AI?
Well, it tells us we need a new way of thinking. First, letting AI learn from the open internet is amazing, but it's fundamentally risky. Second, the most dangerous attacks aren't going to break the system, they're going to use the system's own logic against it. And that means our defenses have to get way smarter. We can't just check the data anymore, we have to watch its behavior. This all points to a whole new equation for trust and security in AI.
You know, the researchers themselves put it perfectly. They said, if we're going to build AI using data from untrusted places like the web, we can't just cross our fingers and hope for the best. We have to design our systems from the very beginning with specific defenses tailored to stop these kinds of poisoning attacks.
And that really leaves us with the final, critical question. As these AI systems get more powerful, more autonomous, and more woven into our daily lives, the fundamental challenge isn't just going to be about making them smarter. It's going to be about figuring out how we can ever truly trust what they know.